Hello everyone. First of all, I would like to welcome you all to this session. My name is, a quick introduction about myself. My name is Aditya and I work as a software engineer at Verizon Digital Media Services. And as a part of this session, as you can see, the topic for this session is video experience operational insights in real time. So in this session, I'll be talking about our operational insight platform, which is powered by Redis. Now this platform is a real-time platform that is used by our operations team, especially during say a global scale live stream of an event where we are expecting millions of users to be engaging with the stream at any point of time during the event, so that our operations team can detect if there are any issues that are impacting the user experience as they are engaging with the stream, and they can then assess and mitigate those issues as soon as possible in a matter of few seconds, thereby minimizing the resolution time as well as the disruption time for our end users. Now, this particular platform collects a lot of different metrics in real time, and few of the categories, like we definitely want to categorize these metrics into, at a higher level into different categories. And one of the category of the metrics is, say, the quality of experience. So obviously we want to know during a live stream, what is the quality of the experience that is being experienced by the users as they engage with our content on our different brands. And few examples of the metrics that we collect in this category are, say, playback errors. So we want to know how many errors that the users are experiencing as they are engaging with the content in real time. Another example of the metrics that we collect is the rebuffer ratio. So rebuffer, to define rebuffer, it's basically the amount of spinning wheel in layman's term that you encounter when you are engaging with a video content. And this usually happens when your content is not loading fast enough for your video player to play. And this is one of the most important metrics that we collect in using our platform. Now, apart from this, we also want to know what is the scale of the audience engagement. So, for a large-scale event, obviously you are expecting audience engagement at any point of time during the event in order of millions, and we want to know what is the scale of that engagement. We want to know, what is the breakdown of that number by, say, different brands of our company. And I'm going to talk, a bit in detail about what brand means. But to give you an example, like, say, AOL or Yahoo front page is basically an example of the brand where the content is served. Then we also want to know what is the video number of video views that are generated, say, from different devices like iOS or Android or connected TV or smart TV. Now, before I start, let me talk a little bit about our company. So VDMS, or Verizon Digital Media Services, is basically the digital media services division of Verizon, which offers one of industry's leading end-to-end platform for our customers who are basically the content owners or the right holders to prepare, deliver, display and monetize their content by engaging with audiences globally on our platform. Now, in terms of content, we are primarily talking about video content. So we are talking about, say, on-demand videos. We are talking about live streams. We are talking about video ads, as well as few other types of content. Talking about some of the services that comprises of this platform. So primarily, we have 4 different services. Uplink is our video streaming service, which basically provides an online video encoding infrastructure for our partners, so they can slice their content, and that content can be made available globally to all the audiences. In terms of delivery, we are talking about content delivery networks, and Edgecast is one of our content delivery network. This is one of the leading content delivery network, which provides a faster, more reliable and a secure way to deliver the content, get the content closer to where the user is. Then we also have monitoring and compliance capability. The platform is basically Volicon, which provides the monitoring and compliance for ensuring quality of experience on every device. And finally, we have the content intelligence service, which is the Media Experience Studio, which provides the intelligence to drive business and technical decisions to optimize certain workflows for our partners. Now, talking about some of the brands that are powered by VDMS. So VDMS powers a lot of brands that includes like both our company's brand as well as our partner brand. Specifically to mention Oath brands, few of the Oath brands have been listed here. So you can see each of the brand is a global brand in itself, where we are expecting millions of users to be engaging with the brand on a daily or a monthly basis. And this means that our partner can now engage with those audiences on any of these brands. To give you an example, let's say we have a partner who wants to stream a sports event, then we are going to surface the content for that partner on, say, Yahoo Sports. Or if we have another partner who wants to stream a finance event, then most probably we are going to surface that content on Yahoo Finance. Or let's say there is a requirement where our partner wants to reach out to wider audiences globally, then we are going to surface that content on multiple different brands at the same time to satisfy that particular requirement of wider reach. In terms of other brands, we also power, say, some of the ad platforms of Oath. That includes Yahoo, Gemini, and Brightroll, and few other brands like HuffPost and AOL. Talking about partner brands, VDMS also powers some of the partner experiences. So we have partnership with some of the major station groups like Viacom and cable operators like Disney, Discovery, ESPN. And in terms of numbers, Uplink, which is our video streaming service, we have streamed around more than 35,000 live events just in last year, and having 400 odd channels. And Edgecast, which is our content delivery network, we are talking about a total capacity of 45 terabits per second, which itself talks a lot about the scale at which we operate. In terms of devices, we have our presence pretty much on most of the devices. That includes like mobile, connected TVs, smart TVs, and web. Now, talking specifically about global scale live event and the challenges associated with streaming such an event. Now, streaming flawless video content to large-scale audiences globally is especially challenging, considering that the event being streamed is a global-scale event where you are expecting millions of users to be engaging with the stream, and this is a live stream at any point of time. So anything can go wrong during the event, and this means that you have only one chance to perform, and there are no second chances. So it becomes all the more important that you collect real-time signals in your ecosystem to detect if there are any issues that might be impacting the user experience, especially from the video stream. And you can then, detect those issues, assess those issues, and mitigate those issues as the event is in progress. So one example of a typical global stream that we basically streamed in the year 2017. You can see the numbers here. It was a global event. It was a sports event for one of our major partner. In terms of event duration, the event was streamed for almost 6 hours. So for the entire duration of 6 hours, you are expected to deliver the content in a flawless manner to large-scale audiences. In terms of brand, we are talking about our company's brand, where the content will be made available, as well as the partner brand. We had around 10 plus brand on which this content was available. Some examples of the brand I mentioned earlier, like Yahoo Sports or Yahoo Front Page or AOL or any of our partner brands. In terms of audience engagement, the most important part, at any point of time during the event, you can expect audience engagement in order of millions because this is a global event. And finally, in terms of devices, obviously we need to have that experience on multitude of devices, and we had 10 plus devices where the experience was made available. Talking about the source of our stream. So video player is obviously the source of our stream. So this is how a typical video session looks like from, say, a video player perspective. When a user engages with the live stream on any of our Oath brand, so you have a unique video session that gets created for that particular user view. And the video player keeps on emitting a set of events or beacons, as we call it, in the background. And all these events are associated with that particular video session. Now, each of the event that is dispatched by the video player contains some critical information about the progress or the performance of the stream. And it is from this information that we try to derive our metrics in real time for our operations team to consume. So all this data is basically the data on which we run our aggregations in real time, and our event collector service collects that data, and our backend infrastructure will run aggregations and then finally generate the metrics. Talking about some of the examples of the events, so you can see start event is usually fired at the dispatched at the beginning of the live stream. Then you have the complete event that is dispatched at the end of the stream. Then we also have what is called as the view event that is dispatched few seconds after the start, and by industry standard this is somewhere around 3 seconds, and this is used to count the number of video views. Then we also have a few events that are dispatched every now and then. So you can see the progress event getting dispatched by the player anywhere between 20 to 30 seconds. And this reports the progress of your stream. And all these events are ultimately collected by our infrastructure. Talking about our platform, so this is how our current video operational insight platform looks like. So where we have the video player, as I mentioned earlier, sending a stream of event to our infrastructure. Now we have event collector service, which does the process of collecting these events. We have 3 different downstream systems where this event collector service writes to. So you can see 2 of them here. So the first system is obviously our operational system, which is purely based on Splunk. So we are looking at raw data. So event collector service is collecting the event, writing the events to log files, and this information is then sent to the Splunk indexers, and finally that information is available on the dashboards. That is used by our operations team. Then we also have a batch processing pipeline. This is not being shown in this particular slide. This is out of the context of the real-time discussion. So this is a typical batch processing pipeline where the results of the aggregations are available after a delay of say minutes or hours, because we are looking at correctness of data, we are looking at enrichment and sessionizations and things like that. So the event collector service also writes to that particular downstream pipeline. And the third pipeline, which is relevant from the discussion of this particular session, is our Redis pipeline. So the event collector service also writes to the Redis-based pipeline, where the results of your aggregations are available in a matter of few seconds. And this is basically the system that is being used today, even in production, to monitor, say, any global scale live events. Talking a little bit about our past. So in the year 2015, we had enabled one of our partners to stream a global scale event, where again we are talking about audience engagement in order of millions at any point of time, the experience being available on multiple different brands of our company as well as our partners, the experience being available on multiple devices. And at that point of time, we had our real-time pipeline, which was purely based on looking at raw data. So we were using Splunk. And because of the sheer volume of the data, so we are talking about around processing 20 million events over 1 minute of bucket every few seconds, and the sheer size of the data as well, we face certain challenges with respect to scaling that system. So what used to happen was, for a global scale event, our real-time dashboard would start falling behind time, and we would not get the insights in real time. And during that time, what we decided was we adopted a very simple strategy, which was we started doing sampling. So we were looking at only say 10% of the data of the raw event to generate our real-time metrics. However, again, there were limitations with that because we are not looking at the complete data, right? So fast forward to 2017, we decided we had another opportunity of scaling a similar scale event. It was a major sports event for one of our big partner, and we decided to revamp our infrastructure. Some of the pain points were, how do you aggregate such a large amount of data in small intervals of time? And for that, we decided to use Redis as a pre-aggregator, an engine in between, to pre-aggregate the data, and this ultimately reduced the amount of data that we had to aggregate in terms of the amount of data as well as the size of the data. And the result of that was we were able to generate our metrics in a matter of few seconds. We are going to look at this particular part in detail. So Redis, why do we use Redis? So as I mentioned, we use Redis as an in-memory pre-aggregator to pre-aggregate the data. Specifically, we use Redis on our event collector boxes. Redis, because of its single-threaded nature, we all know this, that it provides high throughput and low latencies. And obviously, low latencies is relevant from the perspective of real time, and high throughput since we are using Redis on our event collector boxes. Apart from this, Redis also provides some of the advanced data structures. We use sorted set, for example, that is provided by Redis to represent, say, time series in memory. And the other data structure that we use is the probabilistic data structure, which is HyperLogLog. So HyperLogLog allows you to, say, count the number. It allows you to count unique, items in an unbounded stream of data using very limited memory. I'm going to talk about this specifically in the subsequent slide. And we use this data structure to calculate the number of unique video views that are generated, in a particular granularity of time. Now, before that, talking about few examples of the operational insights that we gather in real time. Obviously, quality of experience is one of the categories. So we want to know, for example, what is the quality of the stream that the user is experiencing, and few examples of the metrics are the playback errors. So we want to know how many errors that the users are experiencing. We also want to know, say, what is the startup time. So startup time is defined as the amount of time it takes for your video content to load, and the more the time it takes, the more likely your user is going to leave that content. So it is another important metrics that we gather. Apart from this, the most important metrics that we gather is the rebuffer ratio. So rebuffer, we all know when we are watching a content, whenever you see the rebuffering, so that is what is basically the rebuffer. And we need to keep that rebuffering as low as possible, below certain limits. So from our operations team's perspective, it is very important that we know what is this rebuffering ratio for, say, large scale events in a matter of few seconds, so they can take some action on it. So rebuffer ratio is defined as the percentage of viewers' time specifically spent watching stall playback. And in order to calculate this particular ratio, we collect two different metrics. So the first metric that we collect is the rebuffer duration, which is the amount of time for which the actual rebuffer has happened. And the second is the playback duration, which is the total playback duration, and it is given by a formula, like ratio of these two particular things. Now, from the perspective of a global scale event, our operations team wants to know, say, what is the rebuffer ratio by different content delivery networks. So in our ecosystem, we rely on multiple different CDNs to deliver that content. So it's absolutely critical to know how the performance of one of the CDN is impacting the rebuffer ratio for the users that have been served from that particular CDN, so that our operations team can, in case they detect if there are any issues with that CDN, they can in real time redistribute the traffic to other better performing CDN, thereby minimizing the disruption for our users. So this is one of the most important metrics that we collect as a part of this particular pipeline. In terms of some other examples of the categories, obviously we want to know what is the scale of our audience engagement, so specifically I'm talking about video views. So when a live stream is in progress, we want to know how many video views were created at any point of time, and we calculate that by looking at the video session ID. And as I've talked about video session ID in the previous slide, where the video session ID gets created when, say, a user engages with our content on any of our brand. So we use that to calculate our concurrent views. And we obviously want to know what is the breakdown of this dimension, this particular metric by different dimensions. Like we want to know how many video views were created from Yahoo Sports versus AOL or, say, partner brands. Or we want to know how many video views were created from mobile devices versus, say, desktop or any other connected TVs or smart TVs. So this is also another important metrics that we gather. Talking about some of the challenges associated with developing a real-time system. Now, real-time can mean different things in different contexts or use cases. As far as we are concerned, we are talking about real-time in order of few seconds. To give you an example, let's say if we have in time series example, if there is a event that happens at time t1, and in our case, that event is the degradation of the user experiences. So we are talking about millions of user experiences. So now we are talking about processing all that data associated with millions of users, and there is a processing time involved. So T1 plus the processing time is when you will come to know something happened at T1, or for that matter even before that. So the challenge is always about reducing that processing time as much as possible, especially considering that we are processing around 20 million events for one live event every few seconds. This is how our real-time window looks like. So currently you can consider our aggregations as a sliding window aggregation. So we have a size of the window, slide of the window. The size of a window is 1 minute in our case. So at any point of time, we are looking at 1 minute's worth of data, and that roughly is around 18 to 20 million events, raw events, in that particular bucket. In terms of the slide, we managed to arrive at around 6 seconds of slide. So this window will keep on moving, and every 6 seconds you will generate the metrics. So if you are an observer, so from the window of observation, you will generate a metric that will be generated more or less looking at last 1 minute's worth of data, and this view will get refreshed every 6 seconds. So your aggregations are running every 6 seconds on that amount of data. Some examples of dimensions and metrics that we gather and how we represent that information in Redis. So obviously timestamp is the time when the event arrives on our event collector box. So this is the time, this is basically the processing time. Video ID is the ID that uniquely identifies the video stream that is being streamed on different brands. We depend, in case of CDN, we depend on multiple different CDN. Hcast is one of our leading CDN. We do have other CDNs that we rely on. In case of brands, obviously these are basically the places where your content will be streamed and available. Yahoo Sports has one of them. AOL can be another example. In terms of devices, obviously different devices like iOS or desktop. And finally, the most important thing, the metrics that we calculate. Concurrent is basically concurrent is the number of unique video views that we calculate using the HyperLogLog data structure in Redis. And for other metrics, for calculating, say, the rebuffer ratio, which I explained earlier, we collect rebuffer duration and watch duration. These are two other metrics, and they are, they are simple increment by commands. Now, each of this row gets represented in Redis as a key, and you can see an example that is mentioned here. So timestamp is a part of the key, followed by the names of the dimensions and their values, and finally the actual measure. So one thing to remember here is the cardinality of the keys will be a factor of the cardinality of the dimensions and the measures that you shortlist at any point of, depending upon your use case. And that will be, that amount of data will be available in Redis memory for that granularity of time. So this is an important part to remember. So looking at our architecture, so video player, as I mentioned, is a source of our stream, sending a stream of events. Our infrastructure is obviously behind a VIP or a load balancer, so events can land on any of the event collector layer. So there are three different layers here. So the first layer is our event collector layer, which does the process of collecting the events for processing. Then we also have a Redis cluster. So our Redis cluster is made up of two parts. So we have the master node where the writes are happening, and we have the slave nodes where we run certain aggregations. And there is a sync that happens between these two. The third layer is basically our indexing and dashboarding infrastructure, which is based on Splunk. Now let's look at each of the layer in a bit of detail. So on the event collector layer, you have event collector boxes, and on each of these boxes there runs an event collector service, which does the process of collecting the event from the video player. Also running on this particular box are few local instances of Redis, and we use those Redis instances to do local aggregation on the event collector box itself. So every event that is processed by the event collector service is returned to the local Redis instance for live events, and this means we are doing a streaming write for every event that arrives on this box. And after a particular granularity of time, once our local aggregated results are available, then a local process that is running on this box that you can see here, it will read all those results, and it will then write those results to the global Redis cluster for running our global aggregations. So the read and the write in our case happens once per interval, and that is 6 seconds. Now all the data associated with a particular key, and when I say key, I mean the dimensions and the measures that I have shown earlier. All that data arrives on your master node, and all of that data will get synced to the slave nodes as a part of the standard sync process. And on the slave node, basically this is where we do our actual global aggregation. So there is a global aggregator process that runs on this particular machine, and that will basically run your global aggregations on all the data that has arrived from all the different event collector boxes for a particular key, and it will generate the result, and it will basically dump that globally aggregated result to a log file. So and this dumping again happens once per interval of 6 seconds, and now you have all your global results in the log file on each of your slave nodes. And from here on, our standard Splunk infrastructure kicks in. So we have Splunk forwarders installed on the slave nodes. and they are looking at this content and forwarding this content to, say, the Splunk indexes for indexing. And ultimately, the results of the aggregations will be available on the Splunk dashboard for our operations team to consume. Now, in terms of the different layers and the scale, aspect of scaling them up. So obviously, our event collector layer can be scaled up by adding more machine, and we usually provision based on the RPS that is expected, which is a factor of the rate at which the player is emitting the events, and also the scale of the audience engagement. As far as the Redis cluster is concerned, the second part, we provision our cluster in such a way that basically that's a factor of the cardinality of the dimensions and the measures that we shortlist, and also how spread out or how big is our event collector layer. So that will determine the provisioning on the Redis cluster. In terms of partitioning, we use Redis at 2 different layers. So obviously we have to partition at two places. So on the local Redis, we partition based on the video session ID, and this ensures that we are distributing our traffic evenly across the local instances, and not one single Redis instance is becoming a bottleneck to ensure that. In case of global Redis cluster, we partition based on the key, which is dimension and measure, and this ensures that to run our global aggregation, we need all that data to come or arrive on the same master node, and this basically takes care of that. So all your data for a particular key will come on the same node, and you can run your aggregations, which we are going to see like exactly what I mean by this. Now talking about HyperLogLog, so I just wanted to know how many of you have used HyperLogLog in production. Okay, so HyperLogLog is basically a data structure that is used to count the number of unique items in an unbounded stream of data, and it's an approximate data structure. Now, so basically, let's say in our case, we want to calculate the number of unique video views that are generated based on the video session that's created for a particular user view. Now, if you are not using HyperLogLog, then this means probably you need to store all those video sessions. So we are talking about millions of video sessions somewhere. So you can do a lookup on a subsequent video session to say whether it is already in the set or not, and find out whether what are the unique. But this means that you need memory that is proportional to the cardinality of the keys that you are measuring, and this may not be practical when you are talking about real time. So HyperLogLog is a set of it belongs to a set of algorithms where it will give you an answer, but that is an approximate answer using very limited memory and with a standard error. So Redis HyperLogLog, for example, generates a 64-bit output. So you can count up to 2 raised to 64, which is a pretty big number, with a standard error of 0.81%, using just 12 kilobytes of memory, which is pretty small, considering the amount of data that it can count, unique items that it can count. So the crux of this particular algorithm is it doesn't store the actual value. So in our case, it will not store the video session ID, say. So what it will do is it will use concepts of probability. It will generate a hash which is 64 bits wide, and then it will then try to hash, looking at certain bits, it will try to hash it to some registers, and then it will use some other part of the bits to observe a particular bit pattern, and it will observe a particular runs of zeros followed by 1, and then ultimately store the maximum number that it stores in one of that register. And I think in Redis they use the first 14 bits to index into 2 raised to 14 registers, and the remaining 50 bits are used to observe a bit pattern and store the count. So the maximum value that will store is around 50, and that can be that requires only 6 bits. So you're talking about 2 raised to 14 into 6 bits, and that is how you arrive at 12 kilobytes. And this is a pretty interesting data structure to explore if you want to, say, count the number of uniques using very limited memory. So what are the different operations of HyperLogLog, and where do we execute them in our architecture? So as I said, we use HyperLogLog to calculate our number of concurrent video views. And if you see on the local Redis instance, we execute the pfadd command. So these are HyperLogLog commands. So pfadd, dump, restore, and pfmerge, they are all the commands that are supported by Redis HyperLogLog. And on the local Redis instance, the pfadd will get executed, and it takes two parameters. So one is the key, which is the dimension and the measure, and second is the thing that we are counting on. So in our case, we are counting number of unique video session IDs. And this is a streaming execution, so this is happening for every event. Now, for a particular granularity of time, once your local approximate answer is available on the local box, then we will read that answer using the dump command. So dump will so Redis allows you to serialize the HyperLogLog output of the HyperLogLog, and then it allows you to restore it to some other Redis instance. And we do that for running our global aggregations. So we do a dump and then we do a restore on the remote master. And finally, the most important part, which is the pf merge. This is basically the union operation. So we want to know what is the union of our set, right? So we execute the pf merge on our slave boxes where all the data is available. So to give you an example, like on all your event collector boxes, you will have local approximate answers calculated. So these are your local HyperLogLogs, and now all of them arrive on a particular machine, which is your slave node, and you will execute pf merge on all of those HyperLogLog to generate your global approximate answer. So you are generating a global approximate answer by looking at individual local approximate answers, and this happens once per interval of 6 seconds, and the results are dumped to a log file, and finally they will be available on our dashboards for consumption. I'll walk you through a specific example as to why do we need to do the thing that we are doing with HyperLogLog. Let's say a user engages with our content, a video session ID gets created, and now the player is dispatching events in the background. All those players are associated with this particular unique video session. Let's call this video session as VS. Now let's say the first event that is dispatched by the player associated with that particular video session lands on beacon server BC1 or event collector box BC1. So the event collector service is going to execute your pfadd key vs command, and after an interval of 6 seconds, you will have the output as 1 in this case. So your local approximate answer of 1 is calculated on this box. Now let's say the second event that is dispatched by the player, it lands on the second box, which is BC2. Now since the video session ID is the same and the key name is the same command gets executed on this box as well. So you have pfadd key vs getting executed. So now you have local approximate answer of 1 on BC1 and local approximate answer of 1 on BC2 as well. Now both of these HyperLogLogs will be restored to the master node because of the way we partition our data. So we are partitioning based on the key name. And both these HyperLogLog will then be synced to the slave, and on the slave you can see both these HyperLogLogs being available and the pf merge getting executed. So pf merge accepts the names of both these HyperLogLog to generate the final global approximate answer, and this answer will then be dumped to a log file and ultimately be forwarded to the Splunk indexers and our dashboards for our consumption. So this is a specific example of how we execute the different commands of HyperLogLog in different layers in our infrastructure to calculate the uniques. For all other metrics like rebuffer ratio or starts or bitrate that we calculate in real time, we just use simple increment by. So we are doing local counting and then we are doing global counting. So on the local Redis box, we are doing increment by, and this is happening again on the stream. So this is for every event. Finally, on the local Redis instance, after the granularity of time is over, we fetch the local counted result. Now we increment this, the remote Redis instance by that much amount, and ultimately the global counting happens on the slave box. So we have the results available on the slave box, and then we get this value and dump it to a log file, which is then again forwarded to the Splunk dashboards. As far as Redis redundancy is concerned, we rely on Sentinel setup for our redundancy. So Sentinel is basically a part of the Redis ecosystem, which provides you, high availability. It can do leader election, or it can do, failure detection. So in our case, if you see, there are few machines that are running this Sentinel instance, and they are basically communicating with each other using some protocol. And the moment, say, the master goes down, one of our master goes down, then the sentinel will be aware of that. Obviously, there are certain configs based on the quorum and the majority and things like that. They will arrive at a conclusion that your master has gone down. And once the master goes down, the sentinel will notify our local process, which is actually doing the partitioning, indicating that the master has gone down. Now you need to do something. So our local process will then make sure that it doesn't send the traffic to the failed node. And this is how we basically, ensure availability. Now, one thing I would like to mention specifically is there is a limitation to this system. So what happens in our case is because of the failures, the keys may get shifted, okay, which is not an ideal thing. But since we are talking about real time, and our real time in our case is just 1 minute, the assumption is after a minute of interval of time, this system will auto recover. So you will have disruption on the dashboards for 1 minute, which is the existing limitation. Obviously, there are other aspects of how we can handle this case, where maybe you can move the data, but then again the questions are, if you move the data, there is going to be a time involved in moving the data, and then from the real time perspective, maybe it becomes irrelevant by the time the data is moved and then made available. So in our case, this is how we handle our redundancy. As far as the cluster redundancy is concerned, we have Redis cluster in 2 different regions. What if your Redis cluster goes down? So our dashboards will not be accessible. So for that, we have 2 regions and 2 different Redis clusters, and our local process is writing to both these clusters. And we have the primary and the BCP, and let's say our operations teams, like if the Redis cluster goes down, then our operations team will not see anything on the primary dashboards. They can always switch back to the BCP dashboards because our local process is still writing to the second cluster. Now finally, in terms of the numbers, so before we were using Redis and after we started using Redis, for one live event, we were talking about approximately around 18 million events to be processed, raw events to be processed every few seconds by looking at 1 minute worth of data. As I mentioned, prior to using Redis, we were doing sampling, so we were looking at only 10% of the data, and because of the issues that we faced. And this meant our aggregated events were around 1.8 million. So we had to run aggregations on 1.8 million events every few seconds, so which is 6 seconds in our case. In terms of size, because we were looking at raw data, each event is 1 kilobyte, and the total size was 1.8 GB. Now, after we started using Redis and we started doing pre-aggregations at different layers, for the same amount of data that needs to be aggregated, we were looking now at 100% of the data. So we are not doing any sampling, we were looking at the entire data to arrive at an estimation or a conclusion. For the dimensions and the measures, the cardinality of the dimensions and the measures that we were interested in or we had shortlisted, that translates to around 100,000 events per minute on our indexers to be indexed. Now, since we are looking in terms of size, so since we are looking at only the things that we are interested in, so we only select the feeds that we are, we want, and that means the event size is only 150 bytes, and the total size was 15 MB. So you can see that there was a significant reduction in the amount of data that we aggregate, and also the size of the data, and this helped speed up our indexing when we started using Redis as an in-memory pre-aggregator. Now, talking about the dashboard, so our real-time dashboard looks something like this. So this is the view. This is basically the dashboard that our operations team is looking at on a day-to-day basis. You can see the global metrics being counted and shown on the top. So concurrent views are the number of unique video sessions that are generated in real time. Then you have rebuffer ratio, which is the buffering that is being experienced by the users. Then you also have a few other metrics like impacted view, bitrate, starts, playback errors. And finally, you'll see the breakdown of these numbers by different dimensions. Obviously, CDN is one of the dimensions. So we rely on multiple different CDNs. So you'll see the breakdown of, say, rebuffer ratio by different CDNs. Then we have different brands of our company like Yahoo Sports or Yahoo Finance or say AOL. Then you also have devices, and finally the regions. Now to give you an example, let's say if our operations team wants to know how the performance of one of the CDN is impacting the rebuffer ratio for the users that have been served from a particular CDN, they can look at the combination of CDN and rebuffer ratio. And the moment that they see that the bar associated with that particular one CDN goes up, then that is an indication that there is something wrong with this particular CDN. And what they'll usually do is they'll correlate this information with some other signal from the CDN, and they will most probably, obviously after analysis, they'll arrive at a conclusion that there is some problem with this CDN, and all these users who have been served from this CDN are experiencing this higher amount of rebuffering, and now we need to redistribute the traffic to some other better performing CDN. And this dashboard gets refreshed every 6 seconds, so they get the latest view of the system every 6 seconds. This is one of the important dashboard that our operations team is always looking at for any global events. Talking about this is the final slide. So talking about the results, we were so in terms of end-to-end latencies for the number of dimensions and the measures that we were looking at, we were able to achieve an end-to-end latency of 20 seconds. So from the time the event arrives on the event collector boxes till we run our aggregations on that amount of data which I showed earlier, and finally generating metrics and that metrics being available on the dashboard, so indexing as well as everything, we are talking about around 20 seconds of latency. As I mentioned earlier, we are talking in an order of few seconds. This is the maximum latency, by the way, so our average latencies are much better than this. So I would like to mention one specific event. So what happened was in one of our global scale event, this was a major event, our operations team was looking at this dashboard that we developed, and somewhere in the middle of the event or at the end, there was an issue with one of the CDN, and that CDN started behaving weird, and that started impacting the rebuffer ratio for a large amount of users. And because this system was able to give the signal in a matter of seconds, they were in real time able to detect that there was something wrong with this CDN, and they were then able to correlate this information with other parts of the CDN or other signals from the CDN, and they were finally able to redistribute the traffic, which was kind of it was a big validation for the platform that we had developed. With this, I guess I would like to open this session for any questions if we have, or if we don't have time, then I'll be available after this session for any questions. I think we are out of time, so yeah. So I'll be available after this session for any questions.